In this short set of videos, we're going to go ahead and we're going to go over using the WS2812, which is an integrated controller and LED, and using them to make our own hula hoop. So something look kind of like this. So the idea behind this hula hoop is that if it was spinning really fast, you get some pretty neat patterns. I am not going to demonstrate hula hooping in front of you because I do not have that skill, but maybe you do, maybe you want to build something like it. So we're going to have, this video is going to talk a little bit about timing diagrams and then specifically some details about the WS2812. We have another video which talks about the oscilloscope and then using it for actually analyzing those timing diagrams. And then our final video is going to discuss the actual code that was used on this particular device to make this system. All right, stay tuned.
In this short video, we're going to talk a little bit about timing diagrams so you can understand some of the basic concepts. And then we'll talk a little bit specifically about the WS2812, which is an LED with a built-in controller, and the timing requirements for it. From there, we're going to move on to another video. And in that video, we'll actually show these timing requirements using an oscilloscope and then move into a little bit of the code in yet another video. So let's go ahead and jump into timing. So a little bit about timing. One of the things that we often see when we're dealing with digital logic is we see these beautiful square waveforms. For example, in this image here, the ideal shows that this transition between a low and a high, or a high and a low, is instantaneous if time is on the horizontal scale. It's a perfectly straight edge, it's amazing, and everything happens instantly. Well, as we very well know, this isn't actually true. Nothing can happen instantaneously. Electrons take time, capacitance and inductance in the system can cause ringing and other problems, and so what we actually get is something more like the actual image here on this screen. Now this actual image, just to note, isn't to scale. Traditionally, the high times and low times of a signal are significantly, i.e. multiple orders of magnitude longer than the rise and fall time. However, in order to actually kind of show that edge, we chose to kind of put them together. It's not necessary. You could try to make a system that its rise and fall, its active high and active low times were very close to the rise and fall times, but essentially by that point you're producing more of a sinusoidal wave. This is something you might see in an actual clock signal, but definitely uncommon if you're looking at an actual data signal. So let's talk a little bit about these realistic signals though. If we look at this generalized timing diagram, we have a couple terms that are important to understand. We have high time and low time, as well as rise time and fall time. The high time and low time are the parts of the signal where it's considered to be high or considered to be low. These are usually above 90% of VCC or below 10% of VCC. Rise and fall time, on the other hand, are the time that it takes to transition between either low and high or high and low. And that's usually measured between the 10% and 90% boundary on the signal. Now, in some signals, you're actually going to get a little bit of a waveform, that kind of a ringing effect, where on the rising edge it actually goes higher than the VCC voltage and possibly dips back down, even below the 90%. And this ringing isn't included in the rise and fall time. It's usually part of the high or low time. We always want to try to reduce this ringing as much as possible. Now that we had a little bit of time to talk about the waveforms, let's go ahead and look at the actual chip that we're going to inspect. So the WS2812 is an RGB LED with a built-in controller. It comes from the WS2811, which is a previous chip, which was a separate controller that you then connect an LED to. So in this case, they've put them together into a nice small form factor. They're often sold in strips or other formats. You can see an example of those strips here in this image. And they really make for a simple way to do some really fun color RGB experiments using a microcontroller. There's some great libraries out there, so you don't even necessarily have to know a lot about coding in order to use them. But they also provide us a great opportunity to kind of explore the signal that goes to them using an oscilloscope, which again is what we're going to do in our second video. So if we move on to the timing here, here's right out of the WS2812 datasheet, some of the information about the timing. So this is a unique device in that it uses a single line for controlling the LEDs. And in fact, these LEDs are chained together to create a long string of LEDs where data is passed into the first one and eventually comes out of the last one along the chain. The way they do their bits, either a 1 or a 0 bit, which they then compile into 24 bits of color each, which we'll talk about in the next slide, is using this on-time, off-time ratio. So you'll see from the images here in the text that if we wanted to produce a bit of a 0, we would want to be on for what's called T0H and then off for what's called T0L. If we wanted to be on, or excuse me, if we wanted to represent a logic 1, we'd need to be on for what's called a T1H and then off for what's called a T1L. And if we look at those ratios, this is best seen there in the image, we'll notice that for a 0, the time is shorter for on if we want to make a logic 0, and it's longer if we want to make a logic 1. There's also this thing called a RET code or a rest code. And this code is essentially saying, hey, we're done. You can actually update your screen to whatever data you have, update your LED to whatever data you have, rather than expecting more data to be incoming. So we have to do that as well. Looking at the table of data you see there, you'll see that it has kind of a center timeline, what's expected, whether that be a 0.35 microsecond for a high for the TOH, or a 0.7 microsecond for a logic 1, T1H. But you also have that plus and minus 150 nanoseconds. So technically, you could use that 150 nanoseconds as your rise time. You could have a very slow rise time on the order of 150 nanoseconds or fall time, and the system would still work. Now, realistically, you'll probably never have a rise and fall time of that size, but you could account for it in this system. So to string these together, each LED is 24 bits. And so that means that we're going to transmit patterns of 1s and 0s, which remember are actually highs and lows at specific lengths of time, in the pattern shown here in this 24-bit data. So there's 8 bits for green, followed by 8 bits for red, followed by 8 bits for blue. This pattern, if you look at how long it could take, assuming we transmit either all 1s or all 0s, the time per LED, 24 bits, is about 27.6 microseconds to 31.2 microseconds. So that's something to kind of be aware of because it's going to limit the maximum refresh rate of these LEDs. There's more information about that and a little bit of math that's been done in the materials also provided on the Canvas page related to this video. So what are the pros and cons of this interface? Well, some of the pros is it only needs one data line for communication. This can be really nice if you don't have a lot of data lines or you want to make something small which has a lot of LEDs. And kind of follow on to that, each LED only needs to drive one LED in the chain. So since they're sequenced one after another, the output of one LED passes data only to one other LED. This means that you're going to have very nice clean edges and you can go a little bit faster. On the negative side, of course, you have to have very exact timing. You have to meet that timing restrictions, plus and minus 150 nanoseconds. Also, this particular protocol is really only used by this device. So if you spent a lot of time building a library to handle this type of communication protocol, it would only be useful with these LEDs. So next we're going to go ahead and move on to another video, and in this video we're going to show the WS2812 LEDs, and we're going to look at them using an oscilloscope so that we can kind of see some of these timing constraints.